Good afternoon, guys. Could you let me know if you all are hearing me, please? Okay, guys, great. So I'm gonna start now. So this is our second free session regarding CSEC physics, right? So in today's session, what I'm gonna be focusing on is waves and ray optics, right? Um, CXC kind of indicated what will be coming with respect to this topic, and that is types of waves. You're getting types of waves, right? The speed of sound, reflection, refraction, critical angle, and total internal reflection, right? So those are the things that CXC said, those are the broad topics that it said will be coming on waves. Alright, so for those of you joining for the first time, my name is Terry David, right? I do give online CSEC maths, AdMaths, physics, and chemistry classes. I am a past national scholarship winner. I'm also the author of the official CAPE physics study guides for CXC, right? So those of you interested in lessons concerning physics, you can always WhatsApp me at this number here. A new class will be starting in August. That is for students entering Form 4. All right. All right. So let's get some preliminaries out of the way, guys. Right. Now they said we need to know different types of waves. So based on my experience in terms of what they can ask you in the exam, right? They can ask you to differentiate between what we call a transverse wave and a longitudinal wave, right? A transverse wave and a longitudinal wave. Now, a wave is simply a disturbance in space. That is what a wave is. It's a disturbance in space, right? Now, we can classify waves in different ways. And one of the ways we can do this is by saying a wave could either be transverse or it can be longitudinal. Now, an example of a transverse wave is light. Make sure you know an example for each type. So a transverse wave, a good example is light. And any other wave in the electromagnetic spectrum, they are all transverse waves, right? A good example for a longitudinal wave is sound waves. So don't mix up the two, but make sure you have an example for each one in the exam, right? So light is a good example of a transverse wave, and sound waves a good example of a longitudinal wave. Now, in terms of the difference between those two waves, you need to explain what is the difference. Now, I've given you what you need to say here. So, for a transverse wave, the particles, they oscillate, there's a key word here, at right angles to the direction of travel of the wave. So, what does that mean? It means that for a transverse wave, if the wave is moving in this direction here, right, and the wave is made up of different particles, right? These particles are actually oscillating like this. So the particles that make up the transverse wave, they do this. They move up and down, right? And when we say at right angles to the direction of travel of the wave, so if the wave is going this way, to the right, then they are oscillating at right angles to the direction of travel of the wave. So this here is a transverse wave, right? So this here is a transverse wave. Now, if on the other hand, you have a wave that is traveling this way, right? And again, you have particles making up the wave, but this time the particles are moving this way. They're moving back and forth like this, right? So they're oscillating back and forth like this, right? Now, the easiest way to visualize this is think of a loudspeaker. A loudspeaker is moving back and forth, back and forth. Every time it pushes forward, it compresses the air, and every time it pulls back, it reduces the pressure in the air, right? So the particles that actually make up a sound wave are moving back and forth, right? So this is how we typically represent a longitudinal wave. So this here is what we call a longitudinal wave, right? And this type of wave, in this type of wave, the particles are oscillating in the same direction or parallel to the direction of travel of the wave. So make sure you know these two definitions, because the question that could potentially come is differentiate between a transverse wave and a longitudinal wave, and that's the answer, right? Now, I'm just giving you some brief definitions that you all need to make sure you know. So if they do bring a question on ray optics, you all need to be able to state the laws of reflection. Now, when it comes to ray optics, let's say we have let's say you have a mirror here, right? Let's say you have a mirror here, and you have a ray of light, right? It's traveling towards the mirror, and it strikes this point here. Now, there is something that you all need to be familiar with, and that is something called a normal. A normal is simply a line, an imaginary line, that is drawn at right angles to my surface, right? So this here is what we call our normal. So when we are doing ray optics, right, you need to be familiar with the word normal. So this here, if you were to ask to state the laws of reflection, you're going to use a diagram, and you're going to label your rays. So this ray is moving towards the mirror, so this is called my incident ray, right? That's my incident ray. Now this angle here, I'm going to call it I, right? Now all angles are always measured with respect to the ray and the normal. So I, right, is called my angle of incidence. It's called my angle of incidence, right? Now, when that ray strikes this point here, what is going to happen is that ray is going to be reflected. So this here is what we call my reflected ray, right? Now again, you're going to have an angle here, right, between your reflected ray and your normal, and this angle I'm going to call it R. So this R here is what we call my angle of reflection, right? This is called my angle of reflection. So when they ask you to state the laws of reflection, you're going to draw this diagram for them, label your incident ray, your reflected ray, your angle of incidence, and your angle of refraction. Now, the first law states that the incident ray, the reflected ray, and the normal all lie in the same plane. This is what this diagram is showing. And the second law is that the angle of incidence is equal to the angle of reflection. So that means angle I must equal to angle R, right? That is all that is saying, right? So those are my laws of reflection. The next thing you all need to be able to do if they ask you in the exam is to state the laws of refraction. Now, refraction is simply the bending of rays when you pass from one medium to the next, right? So for example, from air to glass or glass to air, bending is going to take place. So again, there are two laws, and the easiest thing to do here, guys, is to draw a diagram, right? So what you can do, you draw a diagram like this, label this as air, and maybe this one as glass, right? This again is my normal, right? The normal is simply an imaginary line that is drawn perpendicular to my surface. That's all it is. So here's what's happening here. So if you have a ray that is moving towards the glass, right, that ray is going to bend towards the normal here. So this here is my incident ray, right, and this across here is called my refracted ray. So this is my refracted ray, right? Again, you can label your angles. This here is I, and this here is called R. But the thing is, I is called my angle of incidence, right? And R is called my angle. Notice the word is going to change now. It's called angle of refraction. So do not confuse refraction and reflection in the exam, please, right? Because some students, they realize that in the laws of refraction and the laws of reflection, one of the sentences sounds similar. But what is different is you have the word refracted ray here. So the incident ray, the refracted ray, and the normal all lie in the same plane. That's what the diagram is showing. The second law is that the ratio of the angle of incidence, sorry, I wrote something wrong here. Ratio of sine of the angle of incidence to the sine of the angle of refraction is constant. So what that means is that sine I, right? So we're talking trigonometry here now. Sine I over sine R is equal to a constant, right? And that constant here is what we call our refractive index, right? So this is called my refractive index, right? So that's the laws of refraction, right? I just wanted to get these things out of the way first of all before we start to look at some questions. And there's one more thing, right? And those are the conditions for something called total internal reflection. So here's what's happening here. If I have, let's say I have a diagram like this. I have air here, right? And I have glass, right? Now if I have a ray, right, that is moving from glass to air, right, what could potentially happen is that this ray could do this, right? It can escape into air, right? Now this here is my angle of incidence I, right? Now another scenario that we could get is this. Again, you have air and you have glass, right? Now if we increase that angle of incidence in such a way, so we increase the angle of incidence here, right? This is I again, my angle of incidence, but this time your refracted ray is doing this. Instead of entering air, it goes along the boundary between the air and glass. So in this case here, my angle of refraction is 90 degrees, right? So that's a different scenario. And then we have a third scenario here where instead of the ray actually leaving the glass, it stays inside the glass and it does this. So this here is my angle of incidence and this here is my angle of what we call reflection. So this third scenario is what we call total internal reflection. That's what it is. Total internal reflection, right? So this total internal reflection here can only happen under two conditions, right? These are my conditions. The ray must be traveling from an optically dense medium to less optically dense medium. So in your brain, what you need to think about is here. Think of the ray going from glass to air. That's a good example. Going from glass to air, so that's one scenario. And the other condition is that the angle of incidence has to be greater than something called the critical angle, right? So I've drawn three diagrams here. So here in the first scenario here, right, there is something called my critical angle, which we call C. So this is my critical angle, right? So in the first diagram, my angle of incidence is less than my critical angle. So therefore the ray exits into air. In the second diagram, my angle of incidence is actually equal to my critical angle, right? So your critical angle is the angle for which your angle of refraction is 90 degrees, right? Now if we go greater than the critical angle, so let's say my angle of incidence is greater than my critical angle, that is when total internal reflection takes place. Now the syllabus says, so the broad topics they indicated, they said that we need to know about these things, right? Total internal reflection. Somebody asked me if the normal has to be dotted. It can be dotted or it can be solid, right? It doesn't matter. So now we've got that out of the way. Let's have a look at some examination questions here, right? So the first question here, this is January 2012, and look at what they said here. what is the difference between a longitudinal wave and a transverse wave? Now, CSEC says types of waves come in, right? So this could potentially be one of your questions. So all you need to do is to tell them that in a longitudinal wave, the particles oscillate in a direction parallel to the direction of travel of the wave. And then you're going to say a transverse wave, the particles oscillate at right angles to the direction of travel of the wave. So that's my answer for this one here, right? Which is one of the first things that I told you here. So that's my answer from this slide, right? Now, the next thing here now, well, physics has a lot of calculations, right? You're all doing physics in Form 5, you should know that. So they said here's what's going on here. You have a red light, it has a wavelength of 700 by 10 to the minus 9. Calculate its frequency. Now, there is a wave equation that you all need to know, and that is V is equal to F multiplied by lambda. This is what we call our wave equation. Now, the question is asking us to calculate the frequency here, right? So, according to this formula, my frequency, right, is given by V divided by lambda. Now, I know what the speed of red light is, but you may not know, and they may give you that information in the question. So let's see, right. So look at this here. They said the speed of light in air is 3 by 10 to the 8. So you all should be familiar with this number. If you can't remember it in the exam, look somewhere in the question and they will give you that number, right? So the speed of red light, right, is 3 by 10 to the 8. So this is 3 by 10 to the 8 meters per second divided by lambda. Lambda is what we call my wavelength. So this is 700 multiplied by 10 to the minus 9. So one of the biggest challenges that students have when it comes to these types of calculations, they don't know how to use their calculator. That is the biggest challenge. You don't know how to use a calculator, right? So you all could try to work it out for me. I'm going to work it out as well. So it's 3 by 10 to the 8 divided by 700 by 10 to the minus 9, right? And what I'm going to get, or what I'm getting for my answer is this: 4.29 by 10 to the 14, right? And this is in hertz. Now the question, CSEC gives you a lot of marks for physics calculations, and this is how they allocate the marks here, right? Let me show you how they do that. So you're getting 1 mark for using the correct equation, right? You're getting a second mark for substituting your values into the correct equation, and in this particular case here, you are getting 1 mark for your answer, and you're getting 1 mark for using the correct unit. That's why you're seeing 4 marks here, right? So don't try to do any shortcut in the exam. That's not going to help you. You need to put your formula that you're using, you need to put the correct substitution, and you also need to put your unit, right? Now just give me a sec, right? I want to see if I can pull up my calculator here. Let me see if I can, and I can show you all what's happening, right? Hold on a sec. And give me a second. I just want to add are you all seeing this calculator on the screen? All right, so let me make sure and show you all how to do this calculation on this calculator, right? So this is the calculator that I use when I'm teaching, right? So here's what's happening here. You want to work out 3 by 10 to the 8, right? So you're going to press 3 in the calculator. EXP, there's a special button in the calculator that you all need to use called EXP, right? So it's 3 EXP, and you're going to press 8 divided by what are we going to divide by? 700 by 10 to the minus 9. So it's 700. Then you're going to press EXP, and you're going to press 9 minus, right? So it's 700 EXP, and you're going to put minus 9 equal, and look at what the calculator has given me, 4.2857, one long number, right, by 10 to the 14. So my answer here that I'm going to write is 4.29 by 10 to the 14, right? Make sure you all know how to use your calculator properly, right? That is going to be a problem, right, if you don't know how to do that in the exam, right? So let's get rid of the calculator here, right? So that's how we work that question here. Next thing. They said you have to be able to answer something regarding sound waves, right? So here's what's happening here. In this question, in 2010, sound navigation and ranging, right, that's what sonar means, was used to detect the presence of submerged oil plumes in the Gulf of Mexico after a massive oil spill. Figure 7 shows a ship using sonar to locate an oil plume, right? So this is just a big blob of oil inside the ocean that you're trying to find. Right? Now they said, explain with reference to figure 7 how sonar is used to determine the depth of the oil plume, right? And 4 marks for this. Now basically how sonar works is that a sound wave is emitted from some source, right? It's emitted towards some object. The sound waves bounce or are reflected off that object, and it comes back to a detector which is going to detect the sound wave, right? So what you are essentially doing is measuring the time taken for the pulse, the sound wave that is, to go from your transmitter, right, towards the object and back, right? And we can use that time interval to determine how far away this object is, right? So this is what's happening here. So in this case here, you have a transmitter. So you have a transmitter that is producing a pulse of sound. So you have the transmitter here, and the transmitter is producing a pulse of sound waves towards the object, right? So in this case here, it's the plume of oil they're talking about. So the transmitter sends a sound wave, all right, or a pulse towards the oil plume, right? The wave is reflected, right? And it is detected, right, at that point here. Right? So you have some sort of detector that is determining when we receive this pulse, this reflected pulse, right? Now, what we need to do, we need to measure the time taken for that transmitted pulse to return to my detector, right? So you're measuring that time there. Now, the actual formula that we're going to use here is speed is equal to distance over time. Right? You all need to know this from maths as well. Speed is distance over time. So my distance, right, this distance here, right, from where the ship is to where the oil plume is, let's call that D. So D, right, is equal to my speed multiplied by time. Now this speed here is the speed of sound in seawater, right? So this here is the speed of sound, right, in seawater, right? If you were doing this in air, then it'll be the speed of sound in air, right? So that's the speed of sound in seawater. And this time here, you need to be careful with that, right? That time is actually half of this time that you got here, right? Because remember, the pulse is traveling towards the oil plume and back. So the actual time that we need to use here is half this time that you got here, right? So if this time was, let's say, 12 seconds, then the time that I'm going to use in the formula is going to be 6 seconds. So keep that in mind, right? Where am I now? Right? So they said describe, explain how we're going to do that. So you transmit a sound pulse towards the oil plume, right? And you note the time taken for the pulse to return to the transmitter, right? And then you're going to use the formula speed is distance over time to figure out how far away it is, right? Now, well, they give us a calculation here that we should do. So they said if echoes are received 0.3 seconds after being sent, calculate the depth of the oil plume below the detector given that velocity is equal to distance over time. So they were kind enough to give us the formula, right? So that formula is velocity or speed is equal to distance over time. So we want to find our distance. We want to find the depth of the oil. So D, right, is equal to speed multiplied by time. So my speed in this case here, look, they gave us the speed of sound in water. If you all find yourself trying to do an exam question and you realize, wait a minute, I'm not seeing a particular piece of information, just scroll down in the paper, the information might be somewhere at the end of the question, right? So keep that in mind. Now, so my speed is 1450. So they gave us the speed as 1450 multiplied by my time. Now here's what I said. The echoes are received 0.3 seconds after being sent. So that means that you are sending a pulse, right? It is reaching the plumule, right? So the pulse is coming here and it's being reflected. And that time here is actually 0.3 seconds. However, in the formula, the time that you're going to use will be 0.3 divided by 2. It's half that time we're looking for now. So it's 1450 multiplied by 0.3 divided by 2. So let's see. Hold on, let's go back. Let's put back on the calculator here and let's see. So let's clear this, right? And what we want is 1450. So what I'll do, I'll work out is 0.3 divided by 2 first, right? So that's 0.15. That's my time. Multiplied by 1450. And what you're going to get here is 217.5. So you're going to get 217. So this here is 217.5. And distance here is going to be in meters, right? So that's my answer there, guys. Right? So that's how we do a question like that. Chances are you're going to get something similar in the exam because they kind of specify you're going to get something related to sound waves, right? Now, next one here. Oh wait, hold on. I had another one that I was going to give you. Let's do this one first. So your syllabus says that you all need to be able to describe a simple experiment to measure the speed of sound in air, right? So this question is based on that, right? And how do we do that? We have 2 wooden blocks, right? You need 2 people in order to perform this experiment, and you can do this experiment in school actually. So one person, they're going to be striking 2 wooden blocks together to make a sound wave, right? And somebody next to you is going to have a stopwatch. So what you do, you stand in front of a wall. So somewhere in school, you stand in front of a wall, right? And you keep knocking this wooden block. So you're going to produce a sound, but as soon as you produce the sound, the person with the stopwatch is going to start the stopwatch, right? And what the person with the stopwatch is trying to do is to hear when he hears an echo, right? So what he's essentially doing is measuring the time taken for the sound wave to travel from the wooden block towards the wall and back to him, right? And the other thing that you need to know, you need to measure the distance between you all and the wall. That is required. So in this question here, Carl and his friend Tommy were doing an SBA on estimating the speed of sound in air using an echo method. So Carl stands 100 meters from the wall. Carl claps 2 wooden blocks to produce a series of echoes, and Tommy, who was standing beside him, starts his stopwatch. After 1 echo, Tommy stops the watch. This process is repeated, and the time for 50 echoes was calculated to be 30.3 seconds. Calculate the speed of sound generated. Now, I know that the speed of sound is around 330, 340, right? And you should keep that number in your mind. Because if you have to do a calculation and your calculation gives you a number that is, let's say, 600, you know something is wrong with your calculation. So I know the answer should be somewhere between 330 and 340, right? But I haven't worked it out as yet, so I'm going to show you what to do. So they said that the process is repeated and the time for 50 echoes was calculated to be 30.3 seconds, right? So the time, so let's look at that. So what we're going to do, we're going to find the time for one echo. So 50 echoes taking 30.3 seconds. So one echo, right? The time for one echo, right? So 50 takes 30.3. So all we need to do is to take 30.3 and divide by 50, right? And that's going to give me for one echo, right? So let me do that. 30.3 divided by 50, and you're going to get 0.606. So 0.606 seconds, right? So if you all want to see what I just did there, right? All I did was take 30.3 divided by 50 and you get 0.606, right? That's essentially what I did. Now, next thing. Let's just move that calculator here. Now, what we want to do now, we're going to use the same formula. Speed, right, is equal to distance over time. Now, the question is asking us to find the speed of sound. So my distance, right, between those guys, Tommy and Carl, it's 100 meters. So it's 100 meters, that's my distance between them and the wall. And I'm going to divide that by my time taken for one echo. But you have to remember, the sound wave that you're producing is going towards this. It's striking the wall, right? Hold on. It's striking the wall, right? And then it's returning to the guy who's timing using his stopwatch, right? So that time interval to go to the wall and come back is 0.606. But in terms of what I'm going to use in the formula, you're going to use 0.606 divided by 2. You're going to use half that time, right? That is the time taken to cover 100 meters, right? So what some of you all could have done is decided to take 200 meters and divide by 0.606, right? Or you could have said 100 divided by 0.606 divided by 2. So again, I'm going to show you how to do that on the calculator, right? So what I'm going to do here, it's going to be 100 divided by, and I'm going to use a bracket here, 0.606 divided by 2, close my brackets, and my answer is going to give me 330. Remember I told you all, I know what the answer is supposed to be. It's supposed to be somewhere between 330 and 340. So I'm actually getting 330 meters per second, and I know for sure that my answer is correct, right? So that's an estimate for the speed of sound in air, right? So please make sure you know how to calculate this. CSEC says you're going to get sound waves, so make sure you can answer that, right? Oh wait, I now realize somebody had asked why do we divide by 2? It's because the wave has to cover twice the distance, right? That's why we divide it by 2. Alright, so let's look at our next question here. So describe each of the following in terms as it relates to the laws of reflection. So all of these three things here, remember I gave you all a diagram. So this is laws of reflection we're talking about here. So what you should do, you draw a simple diagram. You're going to draw a plane mirror. So this is how we draw a plane mirror, right? You're going to draw your normal, right? So I'm drawing my normal here. So you're going to label that and tell them that's my normal, right? So the diagram itself is going to help explain what these things are. So here is my incident ray. So this here is my angle of incidence. So that's what this is. That's my angle of incidence. Next thing they want, angle of reflection. So all you do, you draw a second ray here and you label this angle here. And this R is my angle of reflection, right? So using the diagram, and using the diagram to explain what each of those things mean. So you're getting 1 mark for each of them. What is the normal, what is the angle of incidence, and what is the angle of reflection, right? So part B now. They said in the description of the formation of an image produced in a plane mirror, right, a physics student recalled 3 features. State 3 features of an image produced in a plane mirror, right? So a plane mirror is as if you're in your bathroom and you're looking at the mirror, you're looking at yourself, right? Now they want 3 features of this plane mirror, right? So one feature is that the image is what we say laterally inverted. It means that when I put up my right hand, when you look at the mirror, it looks like if you are holding up your left hand, right? So the image is laterally inverted. So that is one property or one feature of the image in a plane mirror, right? So one, right, the image is laterally inverted. So the image is laterally inverted, right? That's what that means. Next property, right? When it comes to the image, right? The image produced in a plane mirror is what we call virtual, right? So in the exam they can ask you what is meant by a virtual image. A virtual image is simply an image that cannot be formed on a screen, and also the rays don't actually pass through the image, right? Normally we use dashed lines to represent virtual rays, right? So the image produced by a mirror, right, is virtual. So you're going to say that. So the image is virtual, right? So the image produced by a plane mirror is virtual. And the third property, they only want 3, right? So the image is the same height as my object, right? So the image, so we can put image size, right, is the same as my object, right? So any 3 properties, right? We have a third property where the distance of my object to my mirror is the same as the image to the mirror, right? So that's a fourth one you could have put there. But they just want 3 features, so I'm giving you 3 features here, right? Now, this is related to the same question actually, right? So using relevant physics concept, explain why the word ambulance, right, is painted in this manner in front of some emergency vehicles, right? I've had a student ask me about this and they thought it was a mistake, right? As in they thought the people who were printing this on the ambulance made a mistake, but it's not a mistake. The reason why the word ambulance is written like that is it is laterally inverted. So if you are driving on the highway and an ambulance is coming behind you and you look in your rear view mirror, you will see the word ambulance written clearly on your mirror. That is the purpose of that, right? So the word ambulance is written on the ambulance laterally inverted, so that when the ambulance is driving through traffic, right, a driver looking in his mirror will see the image the correct way, so he can read the word ambulance, right? So that's the answer for part C there. Now let's look at part D, right? I want to focus a little bit on the calculations. So in figure 4, a ray of white light AO, right, incident at 30 degrees. So they gave us, this is 30 degrees here, to the boundary PS. So this is my PS here. This is PS, right? So this here is air, right? And this is glass, right? And what they want? They are saying, part 1, calculate the angle of refraction produced on the PS boundary. So the PS boundary is this one here that I've labeled for you. That's PS. So the angle they want us to find is this angle here. That's my angle of refraction, right? Now, let's see what they said. They said the refractive index for glass is 1.5, right? So glass is 1.5 and we take the refractive index of air as 1. Now, I'm going to show you how I've taught my class to do it, right? So some of you all will use this formula. You always say N is equal to sine I over sine R. If you are comfortable with that, go ahead, no problem, use that, right? But what I've found is that students, they learn of this formula, and then when the ray is leaving from glass to air, they get confused and they're not sure what to do because they use the wrong angles. So CXC also says that we should teach this like this. N1 sine theta 1 is equal to N2 sine theta 2, right? So this is the method, or this is the formula that I usually teach my class how to do this, right? Now, how do we use that formula? So what we do, the N1 is the refractive index in the first medium. So N for air is always taken as 1, right? In glass, they told us to take it as 1.5, right? Now, if you use this method, then there's no way you're going to get this question wrong. So your refractive index in the first medium, which is air, is going to be 1 multiplied by my sine of my angle of incidence, which is 30 degrees. So it's sine 30 degrees, which is equal to N2, which is the refractive index of glass. This is 1.5, right? Multiplied by sine theta 2. Now that sine theta 2 is the angle that they want us to find, right? So I'm just going to call it same theta 2. So what we're going to do, we're going to rearrange this formula. So sine theta 2 is going to be equal to sine 30 divided by 1.5, right? So sine theta 2 is equal to, and here's what we're going to do. I'm going to use my calculator at this point to work that out, right? So let's clear this. Let's shift this calculator a little bit here, right? So it is sine 30 divided by 1.5. So that's what I'm going to do. Sine 30. So I'm going to press sine 30. You're going to press sine first, right? Sine 30 divided by 1.5, and I'm going to get 0.333, right? So I'm going to write that. So you're going to put 0.333. So you write that to 3 decimal places. Therefore, theta 2 is equal to sine, arc sine, sorry, 0.333. So therefore, theta 2. Now you already have that in your calculator. So all you need to do, guys, is just press second function, right? So all you're going to do is press second function. That's this button here, right? And you're going to press sine, and you're going to press equal. And that's going to give me my angle there of 19.5 degrees, right? So my angle of refraction here is 19.5 degrees. So that's my answer for this part, 19.5 degrees, right? So some of you all may use this formula, and that's fine. You're going to get the same answer either way, but it's 19.5 degrees. Now let's see what do we have to do again. So the next part now, they said name the angle of refraction produced on boundary QR. Right? Name. That's a strange question. Name the angle of refraction okay, so what I'm going to assume that they want us to calculate the angle of refraction, right? As in this angle here, right? That's what I'm going to assume they're asking me here, because I'm not sure what they mean by name the angle of refraction. That's weird, right? I would say calculate the angle of refraction at the boundary Q, the QR boundary. That's this boundary here, right? So in which case, what is happening is that the ray is moving from the glass into air, right? Now here's what's happening here. For this part here, there's no need to do a calculation, right? So if this angle is 30 degrees, you already worked out this angle here. You got this angle here as 19.4 degrees, right? Now what that means is that this angle across here, that's the angle of incidence at the QR boundary, is 19.4 as well, right? So this angle here is 19.4 degrees. I'm using normal geometry to figure that out, right? So those two angles are alternate angles because it's a rectangular glass block that we're talking about here. So 19.4 is my angle of incidence. Now, if you are moving from glass to air, and your angle of incidence is 90 degrees, what is going to happen is that this angle here has to be 30 degrees as well. You started off at 30 degrees, this angle here is also going to be 30 degrees. So some of you may be saying, so how you can assume that, right? Well, if we don't want to assume that, we can do the calculation to prove that, right? And let me just get a blank sheet. And I will show you, I'm going to get that same answer, right? I'm going to show you that I'm going to get that same answer here. So what's happening here is that you have this boundary, right? You have your normal, right? Let's look at the diagram again. And this here is 19.4. So this here is 19.4 degrees. That's this angle here. And what you are trying to work out, you're trying to work out this angle here, right? You're trying to work out this angle here. So this here is glass, which has a refractive index of 1.5, and across here you're going back into air, right, which has a refractive index of 1. So if I use the same formula again, n1 sine theta 1, right, is equal to n2 sine theta 2, right? So let's start. You're in glass initially, so the refractive index here is 1.5 multiplied by sine 19.4 degrees, right, is equal to n2, which is the refractive index for air, multiplied by sine, we don't know what this angle is, that's what we're trying to work out, sine theta 2. So this is sine theta 2. So if we rearrange this, sine theta 2 is equal to 1.5 multiplied by sine 19.4. So therefore sine theta 2 is equal to, again using a calculator. Oh sorry, I didn't realize I was blocking the screen. Right? So what we're going to do here, I'm going to say 1.5 multiplied by sine 19.4, and you're going to get 0.498. So this here is 0.498. So therefore theta 2 is equal to arc sine of 0.498. So therefore theta 2, so let's see what we get for this answer here. You already have that in your calculator, so just press second function, sine equal, and look at what you're getting here. You're getting 29.8 degrees, or approximately 30 degrees, which is what I said at the beginning, right? Just by looking at the diagram, I knew that this answer here had to be 30 degrees, right? So that's why they only give you 5 marks for this, right? Yeah, so sorry about that, the calculator was blocking, don't worry. Right, so let's look at, I'll tell you which questions I want to do though. Alright, so this is an older paper, right? Let's look at this question here. So we have a light pipe, right, or what we call a fiber optic cable, right? So most of you all have internet at home, right, whether it's Flow, Digicel, or TSCT, right? Fiber optic cables are what we use in telecommunications. We transmit light in glass fibers. These glass fibers are extremely small. They're small like a strand of hair, right? So basically we are transmitting data at the speed of light, right? So that's how telecommunications companies, how they transmit data, right? So that's an optical fiber here we're looking at. So here's what's happening. So in this question, right, the figure above represents a ray of light leaving the light pipe through the face YZ. So this is the ray that they're talking about here. This ray is leaving here. Now the light ray is incident at M. So we have a ray hitting this point M here, right? At an angle of incidence of 68 degrees. So they label it already for us. This is 68 degrees. That's my angle of incidence. They're also telling us that the critical angle for glass is 42 degrees, right? And in part 1, they want to know what is the refractive index of glass. So something that you all need to know, if in a question they give you what the critical angle is, you can determine what is the refractive index, right? Somebody's asking if I'm covering all the wave topics. Now I'm covering topics that I suspect may be coming in the exam, right? Because they gave us the broad topics, so that's what we're working with, the broad topics, right? So they want the refractive index. So here's what's happening here. There is a formula, right, where n is equal to 1 over sine my critical angle. That's a formula you all need to know. Refractive index n is equal to 1 divided by sine my critical angle. So all you're going to do here is say 1 divided by, they told me what the critical angle is. It's 42 degrees. So sine 42 degrees. So all we're going to do here now, we're going to use our calculator to work that out. So let's see. So we're going to say 1 divided by sine 42, and you're going to get 1.49, right? Or if you put 1.5, that's fine, right? So I'm going to put mine as 1.49. So 1.49. So by the way, just to write this down, you're going to get something like either 3 or 4 marks just for that, just for working out that. So the next part, they want you to calculate the angle of refraction at the face YZ. So let's see how we're doing that. So the angle of refraction at the face YZ, this is my face YZ here. So the angle that they're asking us to work out is this angle here, right? That's what we want to work out. So here's what's happening here. Your critical angle is 42 degrees. Now this angle of incidence here, now remember there's something called total internal reflection. And that happens when a ray is moving from a dense to less dense medium, right? So in this case, if you're moving from glass to air. So this original ray here is starting inside glass, right? You have air on the outside here. So that's one condition met already. The critical angle is 42 degrees. This angle of incidence here is 68 degrees. Because that 68 is bigger than 42, it means that the ray is going to stay inside the glass. So that's why you see this ray does this. The ray stays inside of the glass. It doesn't escape at this point here, right? It stays inside the glass. And that is called total internal reflection. So if this angle is 68 here, it means that this angle here is also 68 degrees, right? Because reflection is taking place. So if on the left is 68, on the right hand is going to be 68. So what that allows us to do is to figure out this angle here. This angle here is my angle of incidence at the YZ boundary. So you all need to work this angle out. So that angle is simply going to be 90 degrees minus 68 degrees, right? And that's going to give us, what is that? 90 minus 68. And that's going to give us 22 degrees. So this angle here is 22 degrees. That's important to us because we're going to use that now. So I know that is 22. I need to figure out this angle here. So I'm going to use the same principle again. And this is the formula that I'm using. Sine theta 1. N1 sine theta 1 is equal to N2 sine theta 2. Right? So N1, that's your refractive index in glass. You just work that out. They made you work out that in part 1. So 1.49 multiplied by sine my angle of incidence, which is, you just worked it out as 22 degrees. 22 degrees is equal to N2. When you go into air, N, your refractive index, is 1. So this is 1 multiplied by sine theta 2. Sine theta 2 is what you're trying to find. This angle here is what the question is asking us to work out. Sine theta 2. So sine theta 2 is equal to 1.49 multiplied by sine 22. Right? So therefore, sine theta 2 is equal to, at this point here, we're going to use our calculator, right? So we need to work out 1.49 multiplied by sine 22. Now I have that in the calculator already. So all I'm going to do is press multiply by sine 22, and you're going to get 0.5. I'm going to put that as 560. So I'm going to put that as 0.560. So therefore, theta 2 is equal to arc sine of 0.560. So therefore, theta 2 is equal to, you have the calculator there already. So all you're going to do is press second function sine, and you're going to get 34 degrees as your angle, right? So the angle here is going to be 34 degrees, right? Right, so I hope you all following here. Now this is really a follow-up to my online CSEC physics class, right? So we would have covered this in my online classes already. So this is just a revision basically, right? So for those of you now joining for the first time, I want you to hit like on the channel, right? And I want you to subscribe, right? And you can also share the link to all these sessions that I'm doing here, right? Right, so that's that question. Look how much marks for this, 8 marks, right? You're getting marks for working out the refractive index, and you're getting marks for working out that angle there, 34 degrees. Let's see. Right, so I'm trying to select particular questions to give you guys here, right? So let's look at this question here. So let's look at part 1. Low frequency, right, electromagnetic radiation is used to communicate with submarines. The frequency used is 30 Hertz. If the speed of EM waves in air is 3 by 10 to the 8 meters per second, what is the wavelength of the low frequency radiation, right? Now, we all know the wave equation is V is equal to F multiplied by lambda. The question wants wavelength, so that's lambda. So lambda is equal to V divided by F. So my speed, they said the speed is 3 by 10 to the 8. So this is 3 multiplied by 10 to the 8 all over 30. That's my frequency, it's 30 Hertz. So you're going to use a calculator to work that out. Sorry again, the calculator is blocking. Right, so what I'm going to do here, it is going to be 3 by 10 to the 8, so you're going to press 3 exp in the calculator, 8, right, and divide by 30, and you're going to get this big number here, right? So you're going to write this number in standard form. You're not going to write out this whole number here. So this is 1, 2, 3, 4, 5, 6, 7. So that's 1 by 10 to the 7, right? So that is 1 by 10 to the 7. So this answer here is going to be 1 by 10 to the 7 meters, right? That's my wavelength. It's a very large wavelength here. Okay. Part 2 now. A beam of low frequency radiation is incident upon the surface of C at an angle of 15 degrees. So they gave us this angle here, 15 degrees. You have air and sea. If the speed of the radiation is reduced to 2.5 by 10 to the Hertz in water, 2.5 by 10 to the 8 meters per second, sorry, in water, determine the angle of refraction, and they also want us to work out the wavelength and the frequency in water. So let me get a blank slide for you all here to do that one. Now they're asking us several things in this question here. Right, so there are a few things that they're asking us here. So they gave us this, right? But this is what we know. In the question, they told us, they told us that we have low frequency radiation. Right, so we know the speed of the radiation in air. It's 3 by 10 to the 8. So my speed, so your V1, let's call that V1, is equal to 3 by 10 to the 8 meters per second. Now they said, now what's happening here, let's continue this normal here, right? Now if you're going from air to seawater, you're going to bend towards your normal, right? So this is what's going to happen here. And you're going to have an angle of refraction here. Now in the question they said that the speed of the radiation is reduced to this, 2.5 by 10 to the 8. So therefore my V2 is equal to 2.5 by 10 to the 8 meters per second. Now when it comes to refraction, guys, there are a few formulas you all need to know, and that is this. So sine I over sine R is equal to V1 over V2, but that is also equal to lambda 1 over lambda 2, right? This is an important formula here. Depending on if they give us angles in the question, we can work out refractive index. If they give us speed, we can also work out refractive index. And if they give us wavelength, we can do the same thing. So here's what the question is answered. They said in the first part, they want the angle of refraction. That's what they want. So let's go to that formula. You realize they want us to work out this angle here. They want us to work out, let's call it R, right? So I need to use this part of the formula, but they also gave us speed. So therefore I can use this part of the formula. So in terms of what I'm going to use, I'm going to say sine I over sine R is equal to V1 over V2, right? V1 over V2. That's what I'm going to use. So let's do that. So I'm going to work it on the side here. So sine 15 degrees over sine R, which we don't know, is equal to V1, which is the speed in air, which is 3 by 10 to the 8 meters per second, divided by the speed in seawater, which is 2.5 by 10 to the 8. Alright? So there are lots of physics students who, when they have a question like this, they don't know what to do. All you're going to do here, guys, you're just going to cross multiply. So you're going to say this by this is equal to this by that. So sine R multiplied by 3 by 10 to the 8 is equal to sine 15 multiplied by 2.5 by 10 to the 8. Right? So therefore sine R, so this is strictly maths here now. This is not no physics here. This is maths we're doing here now. So sine 15 degrees multiplied by 2.5 by 10 to the 8 divided by 3 by 10 to the 8. Right? So we're using the calculator to work that out. So sine R is equal to, I'm going to put back a calculator here. Let's show you what to do. So you're going to put on your calculator sine 15, right, multiplied by 2.5. You press the EXP key and you press 8 divided by 3 EXP, and you're going to press 8 again, equal. And what I'm going to get here is 0.216, right? That's what I'm going to put in my working, 0.216, right? So I have enough space here, so let's come up here. So R is equal to arc sine of 0.216, right? So this R here, so again we're going to use the calculator. So all we need to do now is press second function sine, because you already have it in the calculator, equal, and you're going to get 12.5 degrees. So my answer here is going to be 12.5 degrees, right? That's my angle that we are looking for here. Right, sorry about that. I have to keep switching between screens, so sometimes I forget to remove the calculator, right? So it's 12.5 degrees, right? So if you all never saw that formula, you need to know that formula, guys. So that is what they wanted. The first thing they wanted, the angle of refraction. Now the next thing they want the wavelength, and they also want the frequency in water. So they want the wavelength and they want frequency in water. Let me show you how you're working that now. So in the question here, this, do you see this here? This is important. Now you already know, the speeds, right? And the question is asking us about the wavelength, right? Now in the previous part of the question, you did work out the wavelength. You worked out the wavelength in air. You got this figure here, 1 by 10 to the 7. So what I'm going to do, the formula that I'm going to do is V1 over V2 is equal to lambda 1 over lambda 2, right? V1 in air was 3 by 10 to the 8. V2 was 2.5 by 10 to the 8. That's the speed of the wave in water. Your lambda 1 is what you calculated in the first part of the question, which is 1 by 10 to the 7. So this here is 1 by 10 to the 7 divided by lambda 2, which you don't know. That's the wavelength in the water. So to solve for this, you're going to cross multiply. So this is going to be 3 by 10 to the 8 multiplied by lambda 2 is equal to 2.5 by 10 to the 8 multiplied by 1 by 10 to the 7, right? So therefore lambda 2 is simply equal to 2.5 by 10 to the 8 multiplied by 1 by 10 to the 7 all over 3 by 10 to the 8, right? So therefore lambda 2 is equal to, and in this case here, well, I need a calculator again, hopefully not blocking you guys. So that's going to be 2.5 by 10 to the 8 multiplied by 1 by 10 to the 7 divided by 3 by 10 to the 8, and you're going to get this number here, right, which is going to be 1, 2, 3, 4, 5, 6. So I'm going to put 8.3 by 10 to the 6 as my answer. So 8.3 by 10 to the 6 meters, right? So that's my wavelength in water. So that was the wavelength. They said they want wavelength and they also want the frequency of the radiation in water. So to do that, all we're going to do, we're going to use the wave equation. V is equal to F lambda, right? Your frequency is simply V over lambda. Now your speed of the wave in the water is 2.5 by 10 to the 8, right? And you're going to divide that by a wavelength in water, which is this figure here. That is the 8.3 by 10 to the 6, right? Now, here's the thing. At the beginning of the question, they told you that the frequency used is 30 hertz. When a wave is traveling from one medium to the next, the frequency doesn't change. So when I work on my answer, I should get 30 hertz, right? I should get 30 hertz as my answer. So let's see if we are getting 30 hertz as my answer here, right? So let's see. That is 2.5 by 10 to the 8 divided by 8.3 by 10 to the 6, right? And look, I got 30.1. The reason why I'm getting a slightly different answer is because I rounded off the 8.333, right? So I'm getting around 30.1. So that's my answer here, right? So this here is 30.1 hertz, right? So just remember that when a wave is traveling from one medium to the next, there's no change in frequency. Alright, so I'm just going to look and see what was the next question I was going to do. Alright, so the next question that I'm going to do here is this one here. Right? This question here. So all of these are examination questions, by the way, guys. So they said you have a ray of light entering a rectangular glass block ABCD, and they told us the refractive index is 1.5, and they said the angle of incidence of this ray is 60 degrees. So that's essentially what they've drawn in the diagram. The first part, they want us to calculate the angle of refraction at that boundary, right? So let me get a blank sheet here. Right, so what they want initially in the first part of the question, they said calculate the angle of refraction at this boundary, the AD boundary. So what they really want, they want to know this ray here, right? Let's continue this normal here, and this ray is going to bend towards the normal. So the ray is going to do that. That's what the ray is going to do. So we need to figure out what is this angle here. That's what the question is asking, right? So again, they told us that the refractive index for glass is 1.5. So this is 1.5. And the refractive index for air is 1. We always take it as 1. So, guys, you all can use your formula if you want, right? But the formula that I'm using here is N1 sine theta 1 is equal to N2 sine theta 2. That's what we're using. So, N1 is 1 multiplied by sine 60 degrees is equal to N2, which is 1.5 multiplied by sine theta 2, which is this angle here. That's the angle we're trying to find. Right? So if I rearrange this, I'm going to get sine theta 2 is equal to sine 60 divided by 1.5. So therefore sine theta 2 is equal to, so let's see, let's get back that calculator, and what we're going to do, we're going to say sine 60 divided by 1.5, and I'm going to get 0.577, right? So that's what I'm going to put. I'm going to put 0.577. So therefore theta 2 is equal to arc sine. So sine 0.577. So therefore theta 2 is equal to, now you already have that in your calculator, right? It's already there. So all you need to do is to press second function sine, and you're going to get your answer as 35.3 degrees. So this angle here that they want is 35.3 degrees. So 35.3 degrees. That's my answer for this angle here. So this here is 35.3 degrees. That's what an angle is, right? Right? But what I'll probably do, I'll probably take it as 35 degrees, right? In the rest of the calculation, I feel I'm going to take it as 35 degrees. Right? But let's see what else they want us to work out. So that is the answer for this part here. The next part, what is the value of the angle of emergence at the boundary BC? So let's look and see what is really going to happen to that ray. So the ray would have, so the ray is going to do this. It's going to bend towards the normal. It's going to hit this boundary here, hit this point here, right? Now, this angle that we just worked out there, we got, how much we got? All right, we got 35 degrees, right? So we got 35 degrees here. So this here is 35 degrees, right? Now, because the ray is striking that AB here, right? We need to work out what is this angle across here. Now that angle there, right? This angle here, right, is going to be 90 degrees minus 35 degrees, right? And that's going to give me 90 minus 35, and I'm going to get 55 degrees. So this angle here is 55 degrees, right? That's what this angle here is. Now, if you read further on in the question, they said the critical angle for glass is 42 degrees, right? So if that is 55 and your critical angle is 42, it means that this ray is going to be totally internally reflected at this point here. It's going to do this. That's what's going to happen here. The ray is going to be totally internally reflected. And this angle here is going to be 55 degrees. Right? So that's 55 degrees. So because you're striking this boundary here again, you're going to draw a next normal here. Right? Now if that is 55 degrees, it means that this angle here, now pay attention to what's happening here, right? So this angle here, that's this angle here, right, has to be 35 degrees now. So this here is 35 degrees. So when the ray reaches this point here, it's going to bend away from the normal. So the ray is going to do something like this. It's going to do something like that, right? And this angle here, your angle of refraction now, right, that's this angle here, is going to be 60 degrees, right? Now you can show this by calculation, but that's going to be 60 degrees. Is that making sense, guys? Or have I lost you totally? You see, when it comes to rays traveling inside a glass block, it is very important that you all pay attention to the angle of incidence inside of there, right? Because you have to compare those angle of incidences with my critical angle, right? So they said in this part here, what is the angle of emergence at the boundary BC? So this one here, the answer is just 60 degrees, right? There's 60 degrees, and you could show that by calculation. Now, in the third part, they said if the critical angle for glass is 42 degrees, describe what would happen to the ray if it has an what would happen to the ray if its angle of incidence on boundary BC is 42.5. So all they're trying to say there is if the ray, so you had the ray here initially, it's going to be totally internally reflected at this point. But based on our calculation, we know that it is going to exit, the ray is going to exit at that point here, right? But what they are saying now is here what? If this angle here is 42.5 degrees, what's going to happen? Well, if it's 42.5 degrees, it means that the ray is going to be internally reflected, so it's going to do this. The ray is going to stay inside the glass block, right? And then it's probably going to emerge maybe at this point here, right? So the key thing I want you to take from this is that you need to see what is happening to the ray inside the glass block by comparing the angle of incidence to my critical angle. That's what you need to do, right? Now, our next question here that we want to look at here. So look, they've asked this question so many times, and this is a recent-ish paper. This is June 2017. Distinguish between a transverse and a longitudinal wave. So I suspect you all are going to get a question along those lines in the exam. So make sure you know that answer, right? And look at what it said in part 2. Give one example of each. A transverse wave, I told you all, use light as your example. For longitudinal, we're going to use sound. These are easy marks in the exam. Please try to get those easy marks, right? The third part, in the wave equation, we have velocity, frequency, and they want to know what is the wave equation. So V is equal to F multiplied by lambda. So look at this. 2, 4, that's 5 marks just for doing that, right? The next part here, they said a wave motion has a frequency of 10 Hertz and a wavelength of 250. Calculate the speed. So we know V is equal to f lambda, right? And you want to calculate the speed. It's going to be frequency of 10 hertz multiplied by 250. So therefore this here is going to be 2500 meters per second, right? So that's my speed of my wave, 2500 meters per second. So the next thing you all need to be careful with is these types of graphs. So this here is what we call a sinusoidal waveform, right? It's a sine curve essentially. And you have displacement against time, but I want you to pay attention to what time is given here. This time here is given in milliseconds. Now be careful, right? Let me ask you all something. The first part, they said indicate the amplitude of the wave. So amplitude of your wave here, right, is going to be this distance here. This distance here is my amplitude of my wave, which is 0.5. Look at the unit is millimeters. So my amplitude here is 0.5 millimeters, right? Well, that's what I asked you here. Let me ask you all something. What is the amplitude in meters? We already saw from the graph the amplitude is 0.5 millimeters. What is the amplitude in meters? Right, so I'm seeing some answers here, and here's what you need to do, right? Here's what you need to do. So there are some prefixes you all need to learn. You see this milli here? That milli means multiply by 10 to the minus 3. That's what that means. So if you have 0.5 millimeters, here's what that means. That means 0.5 multiplied by 10 to the minus 3 meters. So you can leave your answer as 0.5 by 10 to the minus 3. Or, look at this. What you can do is, so for some reason my connection just went down there for a sec. So here's what you're going to do. 0.5, you press exp to the power and you put a minus 3. And this here is going to be my answer. 0.0005. Right? So 3 zeros and a 5. So your answer here is 0.0005 meters. That's my answer, right? The next thing they want in part 2, they want to know what is the period of the wave in seconds. Pay attention to the little things like this. So let's go back to the wave. What is the period of this wave in seconds? So look at the wave and tell me what is the period of this wave. So these are things you need to be careful with, right? So your period is your time taken for one oscillation. So here's what you have to do from this graph. Your period, right? If you want to start at this point here, let's start at the origin, right? One wave, one oscillation is one crest and one trough, right? So from this point here to this point here is going to be one period, right? So from this point here to this point here, that's one period. So therefore my period, and we have a symbol for that, it's capital T. So period is capital T, and my period here is going to be 4.0, and you need to look at the units. The units here is in milliseconds. So 4.0 milliseconds, right? So that's the first thing you have to be able to get from the graph. What is your period? So your period is 4.0 milliseconds, right? But we need the access for the answer in seconds. So let's go back here. Let's go back to the question. So your period is, how much I said it was? 4.0. So your period here is 4.0 milliseconds. Again, milli means something to us. That means 4.0 by 10 to the power minus 3. Every time you see the word milli, it means 10 to the minus 3 or divide by 1,000. Right? That's what it means. And this is seconds. So therefore my answer here is going to be, so I could show you on the calculator what that means. So let's do this, right? 4 exp 10 to the minus 3 is going to be 0.04, right? So my answer here is going to be 0.04 seconds, right? That's my period, right? Look at how much marks we got again for this here. 6 marks for these 3 parts here, right? That's plenty. And the last part, part 4, they want us to know the frequency. Now this is a formula you all need to know. Frequency is equal to 1 over my period. So obviously if you got this answer wrong, then you won't get the second part correct. So it's 1 over my period in seconds, which is 1 over 0.04, right? So use a calculator for that. 1 divided by 0.04, right? And that's going to give me 25 hertz, right? So my frequency is going to be 25 hertz, right? That's my frequency. Now the last part, now they said state one property of an electromagnetic wave. Now electromagnetic waves, you're also supposed to know the electromagnetic spectrum, right? So you have visible light in the spectrum, you have X-ray, gamma radiation, UV radiation, right? Infrared, radio waves, right? And all of them have similar properties, right? So you have a range you can choose from. They all have the same speed in a vacuum, right? They are all transverse waves. They can all show reflection, refraction. They can even produce an interference pattern. So basically, any property you give them, you're going to get a 1 mark, right? That's not a big deal there, right? So let's see, what's the time here? Now there's one more question that I wanted to show you all, just in case they bring this, right? And that has to do with lenses, because sometimes they like to bring questions pertaining to a lens, right? So let's see. So here's what we have here. Let's get rid of this calculator, which might be blocking. So a stamp collector views a stamp of height 2 centimeters with a hand lens placed 1.5 centimeters from the stamp. The distance of the image from the lens is 5 centimeters. The object distance u, okay, so they gave us the lens formula, right? You all need to know this formula. 1 over u plus 1 over v is 1 over f, right? They want to know the height of the stamp, right? so let's see what we have here. So you know the height of the stamp, right? The lens, so this is what's happening here. You have a lens here, right? And you have your stamp. Let's say this is your position of your stamp, right? And the lens is placed 1.5 centimeters from the stamp. So this distance here is 1.5 centimeters, right? Now, that's what we call U, right? When it comes to this formula, that's what we call U, right? The distance of the image is 5 centimeters, right? So the distance of the image is 5 centimeters from the lens. So the image is in this direction here, right? And that is what we call V, and that is 5 centimeters, right? So you all need to be able to extract this information from the question. So you have U and you have V. Now, here's what the question says. Calculate the height of the image. Now, the way how CSEC asks this question, they did it the wrong side. Because I can't work out the height of the image unless I know what my magnification is, right? So the magnification for a lens is given by V over U. So V in this case here is 5, right, divided by 1.5. So my magnification is actually, I'm going to use the calculator, 5 divided by 1.5, and you're going to get 3.33. So my magnification is 3.33. That's the answer for the second part. Now, the reason why I'm working the second part first is I can't work out the first part unless I know what the magnification is. So that's my answer for part 2. In the case of part 1 now, you want to find the height of the image. There's another formula for magnification, which is this. My magnification is the height of my image divided by the height of my object, right? But you know what the magnification is. So that's what we want to do. We want to find the image. So the height of my image is equal to my magnification multiplied by the height of the object. The magnification, you know what it is? It's 3.33 multiplied by the height of the object, which is 2.0, right? Look, this number here, that's the height of the object. So you're going to just take that answer that you got before and multiply by 2. And what you're going to get for the height is 6.67 centimeters. So that's my answer for part 1. So this is part 1 and this here is part 2, right? The way how they ask us here, you have to work it reverse. The next thing I want to know, what is the focal length of the lens? So 1 over my focal length is equal to 1 over U plus 1 over V, right? So 1 over F is equal to 1 over U, which is 1 over 1.5. So 1 divided by 1.5 plus 1 over 5. So here's what we're going to do. We're going to use our calculator to do this, and I need you to see how I'm doing this, right? So let's get back this calculator here. So on the calculator, this is what I'm going to type. So 1 divided by 1.5, right, plus brackets 1 divided by 5 close brackets equal, and I'm going to get this 0.866, right? So 1 over F, so let's do that here. So I'm going to come across here. 1 over F is equal to 0.866. Oh, that'll be 867, right? So therefore F is equal to 1 over that figure, 0.866. So therefore my focal length of my lens is going to be, I just need to invert this answer. So there is a button on your calculator that can do that. Let's see if I can find it for you all. It is second function, this button here, right? And I'm going to get 1.15 as my focal length. So this here is 1.15 centimeters. That's my focal length of my lens. Right? I know seeing you all asking me something about the frequency. Hold up, eh? Oh, that was the previous question. The frequency here was 25 Hertz, guys. Right? So my answer for the focal length of the lens is 1.15, right? So you all need to know your lens formula, just in case they bring lenses in the exam, right? And the last part of the question, part 4, they said the position of the image formed if the object distance is double. This here is my object distance, 1.5, right? So I'm going to use the same formula again. 1 over f is 1 over u plus 1 over v, right? Now you just worked out the focal length of the lens. You got 1.15. So this here is 1 divided by 1.15 is equal to 1 over u, which is, they said, is double. So you're doubling this figure here of 1.5, and that's going to be 3.0 plus 1 over v, right? So you need to figure out what v is. So 1 over v is equal to 1 over 1.15 minus 1 over 3.0. So 1 over v is equal to, so we're using our calculator for this, right? 1 divided by 1.15, you're going to get that, minus, open brackets, 1 divided by 3, close brackets, equal. So you're going to get 0.536. So this is 0.536. So therefore v is simply 1 divided by 0.536. So therefore v, so I'm going to use, there's a special key that allows me to do that. So second function, this button here, and you're going to get this as your answer, 1.86, right? 1.86 centimeters. All right, so that's my answer for my third part. All right. Alright, that's all. So some of you are saying there's an error in my period. Let's go back to that question. Let's make sure. Alright, so from the graph, let's see the period was 4 milliseconds. So it's 1 divided by 4 by 10 to the 3 minus. Oh, right. So, yeah, you all are correct. Hold on. So this here, this should have been, yeah. Let's fix that. Right? So you all correct. It's supposed to be 0.04 here, seconds. Right? And this will be 0.004. Right? And therefore, that'll be 250. Yeah, good spot, guys. Right? Sorry about that. So the answer is 250. Alright guys, so these are the questions that I wanted to look at today, right? I hope you all found the session or you learned something in the session, right? Because a lot of this material, I covered this in my online classes already, right? So I just wanted to do a few questions with you all, right? So what I'll be doing, we have a session next week around the same time as well, next week Wednesday at 3 o'clock, right? If you're all interested. So I'll probably be doing the next few topics that we need to look at would be things like thermal physics, as well as radioactivity and electromagnetism. Those are the next thing that we need to look at, right? So I hope it was productive for you all, right? And I will see you all next week, right? So on Monday we have chemistry, on Tuesday it's maths, and on Wednesday it's physics, right? So the next session for physics will be next week, Wednesday. Alright, so there's no problem, guys. Yeah, so chemistry will be next week Tuesday, next week Monday, sorry, and next week Tuesday is maths, and Wednesday will be physics. Alright, so enjoy the rest of the evening, guys, and I'll see you all next week.